Welcome to our 34th lecture in Combinatorics. Today we'll talk about matchings. To illustrate this topic, we'll start with an example in which we have a set of workers, as in the picture, for example, 5 workers. Let's call them W1, W2, W3, W4, W5. And you have a set of jobs, J1 up to J5, such that each worker is qualified to do certain jobs. So this situation can be described by this bipartite graph, where we draw a blue edge between each worker and the jobs that that worker is qualified to do. So worker 1 would be qualified to do job 1 or job 3, and worker 5 would be qualified to do job 3 and job 4, for example. And the question is it possible to match each worker with a job that that worker is qualified to do, such that each job is assigned to exactly one worker? In other words, we like to pick a certain edges from this graph. For example, W1, J1, or W5, J3, W3, J2. And in this situation, these are three edges that we can pick such that no two edges intersect, have any common endpoint. So the question for us would be if it's possible to find 5 edges with this property, such that each vertex is contained in one of them. So to make this problem in the language of graph theory, let's describe it as follows. So what we are trying to do, we'll start with first with the notion of a matching. So let's say we have a graph gamma, vertex set V and edge set E. Graph. And we have M, a subset of the edge set, is called a matching. If no two edges in M share an endpoint. So for any E, which is not E prime, in our set M, E intersect E prime is the empty set. So in our example on the top, the edges W1, J1, W3, J2, and W5, J3. This forms a matching. This is a matching. But if I look at the edges W1, J1, let's say W2, J4, and W3, J4, this is not a matching, because we have this J4, which is in both containing 2 edges. Okay, so that's a notion of a matching. And what is the problem that we're interested in? So the problem that we're interested in, we are given a graph, and we'll start first with the bipartite graph, similar to the situation that we're in here. So let's say we have a graph gamma that is bipartite with partite sets A and B. So we have here we have some vertices A, and here we have some vertices in B. So let's assume cardinality of A is less than or equal than cardinality of B. So what we like to find is to find a matching, so a collection of edges, such that every vertex on one side is contained in one of these one of the edges of the match. So let me add a definition here. So if we have a matching M, the vertices contained in the edges of M are said to be saturated by M. Okay. So what we're interested in is, so in the bipartite graph, we're interested in a matching that saturates all the vertices on the smaller side. And why is that? Well, that's the best you can hope for, because so this should be pretty easy. But if we have gamma a graph and M a matching in gamma, then the cardinality of M, the number of edges in it, is at most, so let's say a graph with n vertices, this is at most n over 2. Because if you have any graph and you have the edges in your matching, let's color them, use a different color, choose them green. Potentially you could have some vertices that are not in any edges of this maximum matching, of maximum size. But so in total, the number of edges that we have here, the cardinality of M, is at most the number of vertices in the graph divided by 2, is n over 2. So, okay. There is I'll just add a quick definition here. If gamma is a graph on n vertices, and M is a matching of gamma, M is called a perfect matching if every vertex of gamma is saturated by M. And this is actually equivalent to the cardinality of M being equal to n over 2. Okay, so the larger size of a matching in a graph is half the number of vertices, and the only time you can have equality is so if you have equality, then the number of vertices must be even, but that's not a sufficient condition for the existence of a perfect match. So let me write this down here. Gamma has a perfect matching. Implies the number of vertices n is even. That's clear because this follows since n over 2 is the cardinality of the maximum matching. But the converse is not true. So n even does not imply that gamma has a perfect matching. And there are many examples. The simplest one, consider the complete graph K1, bipartite graph K13. It has 4 vertices, but it doesn't have a perfect matching. Once you use one edge, there's no edge between these two vertices. Okay. So again, let me now come back to the bipartite graph case. So the way we started, we have the bipartite graph with partite sets A and B, and we're interested in a matching that saturates every vertex in A. Okay, that is a problem. Can we characterize such graphs? And it turns out that we can do that. And this is a famous result in graph theory, which is due to Philip Hall. And the result is called Hall's marriage theorem. And before I state it, let me just describe let's see what happens if a bipartite graph has a matching that saturates the small side. So let's say we have, as before, let's say we have a graph with the the smaller side with partite sets A and B, and A is the smaller side, smaller partite side. And we have a bunch of edges here, and so on. And let's say we have a perfect matching there. So I'll draw here some perfect matching, something like this. Okay. Not a perfect matching, a matching that saturates A. So let's assume that there is a matching that saturates A. So what can we deduce from that? Well, one thing we can say is that if we take any subset of vertices on the left side, on the A side, so let's, again, we assume that there is a matching that saturates A. Then if we take any subset S of A, so in this case, S consists of these 3 vertices on the left. Each of these vertices in the set S is contained in one edge of the matching that saturates A. So on the other side of the graph over here, we will have the kind of the corresponding the other endpoints of these edges in the matching. So in this case, S has 3 vertices. We have 3 vertices, 3 distinct vertices on the other side that match with the 3 vertices from S. Now, if we look at the following set, we define it as here, the neighborhood of S. The neighborhood of S consists of all vertices B on the right side, such that B is adjacent to some vertex A for some A in the set S. So in our situation, N of S in this picture, N of S contains these 3 vertices here, but you see it also contains this vertex and it also contains this vertex. But one thing that we are certain that is happening is that because there is a matching that saturates A, that implies that for any S in A, if I look at the cardinality of the neighborhood of S, this has to be greater or equal than the cardinality of S. This is because the neighborhood of S contains for each edge of the matching contains the endpoint in B of that edge. And since we have cardinality of S edges here, the cardinality of S edges from the matching, we must have here cardinality of S vertices, and then the neighborhood of S contains at least these many vertices. So this is a consequence of having a matching that saturates A, and the beautiful result of Philip Hall is that this is actually a sufficient condition as well. So let me state the theorem here. This is a theorem. It's called Hall's Marriage Theorem. I think it was proven in 1931. And it states the following: let gamma be a bipartite graph with partite sets A and B, cardinality of A less than or equal to the cardinality of B. And the statement of the theorem is that there exists a matching that saturates A if and only if for any subset S of A, the neighborhood of S, N of S, has cardinality greater or equal than the cardinality of S. And recall that this is a definition of the neighborhood of S. S is a subset of A, and neighborhood of S consists of all vertices in B that have at least one neighbor, in S. So I think, yeah, it's 35 here. Okay. All right, so how do we prove this result? So the implication, the fact that the existence of a matching implies this inequality, this was, we explained it before here, so this was done. Now the condition here, I'll give this condition a name. I will call this condition, so this condition here, I will call this Hall's condition. So what we want to prove now for the this implication from right to left is that if Hall's condition is satisfied, then gamma has a matching that saturates A. So again, when I say saturates A, it means it saturates every vertex of A. Okay. So how do we prove this? Well, this is a proof that I think originally is due to Paul Halmosh. And so it's a proof, we'll use strong induction. On the cardinality, of the smaller sides, on cardinality of A. Okay. All right, so how does this work? Well, we start with the base case. The base case is cardinality of A is 1. Now, in this case, what does Hall's condition, what does it tell us? Well, it tells us that for any subset, so let's say A is a set with one element, let's call it, not A, let's just say X1. So A is X1, and our condition is that for any subset S of the set X1, the neighborhood of S is greater or equal to the cardinality of S. So I will just, if you take S empty set, you get nothing. 0 is greater or equal to 0. So if you take S to be the set X1, then this tells us that the cardinality of the neighborhood of the set X1 is greater or equal than 1. So that implies that X1 has at least one neighbor. So we have a graph in which on the left-hand side, we have one vertex. So this is the set A, X1. And on the other side, we have set B, in which there's at least one vertex. Let's take one of these vertices. Take one such neighbor, Y1, let's say. And then the edge X1, Y1, that's an edge that saturates, that's a matching that's of cardinality 1 that saturates the left-hand side because there are no other vertices other than X1 to be saturated there. So from there, we get that the edge X1, Y1, it's a matching, saturates A, so we're done. So the base case is pretty much trivial. Now, how do we deal with the induction step? That's where the difficulty is. Induction step. So for the induction step, okay, assume that gamma is a bipartite graph that satisfies Hall's condition And we have that cardinality of A is greater or equal than 2 and is less or equal than cardinality of B. Now here's where the proof, you know, when you see it first time, you may get a bit confused about how it works. But here the proof splits into two cases. So case one is the situation in, so Hall's condition guarantees that the neighborhood of S is always greater or equal than cardinality of S. Case one is when something actually stronger happens. And case one is when for any S in A, but for any proper S proper subset of A, the neighborhood of S is not just greater or equal than cardinality of S, but is greater or equal than the cardinality of S plus 1. Okay, maybe you were lucky and we have this, this stronger condition. So I'll just state case one now, and I'll deal with it in a second. And case two is the complement of case one. On one hand, you have the Hall's condition that the neighborhood of S is always greater or equal than in size than the cardinality of S, but case one is not going to happen. So that means that case two is that there exists S0, a proper subset of A, such that the neighborhood of S0 equals the cardinality of S0. Okay, so I hope it's clear that this is a legit fork in our proof, and these two cases cover all the possibilities. Now let's deal with each of them separately. So let me do here case one. So again, we have this for any S proper subset of A. The neighborhood of S is greater or equal than the cardinality of S plus 1. Okay, so what do we do here? So let's draw a picture. We have our A. So we take one vertex in, so let's pick a vertex A in A. Let's take this A. By applying the Hall condition for the set, condition for the set just by the singleton A, that tells us that the neighborhood of A has cardinality at least 1. So A has at least one neighbor. And let B be one such neighbor. Okay, so let's say we have B, and these two vertices are adjacent. And now here's the intuition of what is going to happen in this case, how you can use the induction hypothesis. We are going to reduce the problem now. We are going to get rid of A and so we'll get rid of A and B and the edges. I mean, there could be some edges incident with, you know, B could have some edges here, A could have some edges here, but we just get rid of all such edges. So we cut them from the graph. We'll get a smaller graph in which is still bipartite, in which the partite sets, their sizes have dropped by 1. So the one on the left side is still the smaller. And now what we want to do is we want to prove that the Hall condition is still satisfied in this smaller graph. And if the Hall condition is satisfied in the smaller graph, we can have a matching that saturates the smaller part. And we can, to this matching, we can just add the edge AB and we will be done with that. Okay, so that's the basic idea here. So let's just write it down. So as before, you have these vertices on this side. Let's say we have these vertices on this other side. This is A, this is B. And now, so let's say gamma prime is the bipartite graph obtained by removing the vertices A and B from gamma. Okay, so like I said before, it's just everything that you will see below the red line. We delete the vertex A, delete the vertex B, and we delete any edges that may involve them. Okay. Now I claim that Hall's condition is true in gamma prime. And how do we prove this? Well, let's take a subset of vertices here. So let's call it T, a subset of vertices in, well, so let me say something first. So this was A and this was B. Now gamma prime has bipartite sets. Let's call them A prime, which is A minus A, and B prime, which is B minus B. Okay. And now to prove that Hall condition is satisfied, let T be a subset of A prime. Okay, so we can take a T here. This is T, and I'm looking at the neighborhood of T in this graph in gamma prime. So I would like to show that the neighborhood of T in gamma prime has cardinality at least cardinality of T. And how do we do that? Well, we use the fact that the Hall's condition is satisfied for the graph gamma, but in this stronger form. So what we do is we take prime, and after that, what we do is we look at they could potentially be an edge. It could be edges between B and T. But what happens is that if we look at the neighborhood of T in the graph gamma, in the big graph, we know that this is greater or equal than the cardinality of T plus 1. Okay. Because we are in case 1. And stronger things happen here. Now the neighborhood of T in gamma, this is at most how much? Well, you could have edges from T to the vertex B, and then so that could be at most 1 there, plus all the other neighbors of T in gamma are the same as the neighbors of T in gamma prime. So that would be the neighborhood of T in gamma prime. So we end up with this expression on the left being actually greater or equal than cardinality of T plus 1, which means that the neighborhood of gamma prime, in the neighborhood of T in gamma prime is greater or equal to T for any T, a subset of A prime. So that implies that our claim is true. And because the claim is true, by the now by induction hypothesis, gamma prime has a matching that saturates A prime. So we will have edges here, more blue edges, that in gamma prime that saturates A prime. And then we just add the edge AB to that, and we get our result. So we have that M prime is a matching of gamma prime that saturates A prime, and then we take M, which is M prime union AB, is a matching of gamma that saturates A. And we're done with case 1. Now, case 2 is the following. There exists a subset S0, let's say, of A, so a proper subset of A, such that the neighborhood of S0 equals the cardinality of S0. So in this situation, we have the following. So again, A is the smaller size. Let's say we have a S0 here, and its neighborhood is this neighborhood is N S0. And then you have another part in this graph, because this is a proper subset. So this part is A minus S0. And you also have another part here, which is B minus the neighborhood of S0. So now what do we do? How do we use the induction hypothesis to get matching in the big graph? So we do something similar. So we break the graph into 2 parts. So in this situation, we will have one graph, let's call it gamma 0, is the subgraph of gamma induced by S0 and the neighborhood of S0. So one thing you should realize is that there are no edges from S0 to B minus NS0, because that's the definition of the neighborhood. They could be, I mean, it is possible to have edges here, but definitely there are no edges from S0 to B minus the neighborhood of S0. So what we want to do is you split the graph into, so that's gamma 0, and gamma 1 is the subgraph induced by A minus S0 and B minus NZ. So even if there are some edges from, like some edges like this, they will not belong to gamma 0 or to the gamma 1 graph. Okay. Now what we're trying to do in this proof is, if we can show that there is a matching that saturates S0 in gamma S0, and if there is a matching that saturates A minus S0 in gamma 1 graph, then we can take these 2 matchings together. We can take the union of them, and we get a matching that saturates A in the big graph. So that's the strategy for this. Now, one part is relatively easy, because you see we have gamma 0 here, and NS0, if you have any vertex inside S0, its neighbors are going to be contained in this neighborhood NS0. So it's relatively easy to show that the whole condition is true for the graph gamma 0. And this follows because whole condition is true for gamma. That implies that whole condition will be true for gamma 0. And because of that, that implies, so that will give, implies that there will be, there exists a matching M0 in gamma 0 that saturates S0. Okay. Now the second part, now we are looking at the other at the bottom part of the graph. So let me draw it again. So this is S0, this is an S0. Kind of cut it up there. And we have here, here we have A minus S0. This is B minus N S0. And we're looking what happens in this graph at the bottom. So gamma 1 is the subgraph of gamma induced by A minus S0 and B minus NS. Okay. So I would like to prove that claim gamma 1 has a matching that saturates A minus S0. To do that, I will prove it by showing that gamma 1 satisfies Hall's condition. And if I can prove that, then by the induction hypothesis, that would imply that gamma 1 has a matching that saturates A minus S0. Okay. So how do I do this? Again, we take a subset here of, let's call it T. Let T be a subset of A minus S0. I want to prove that the neighborhood of T in the graph gamma 1 has cardinality, at least cardinality of T. So the neighborhood of T, this is going to be neighborhood of T in gamma 1. So how do we do that? Well, this is how we do it. We define S to be the set S0 union T. So we tag along S0 to these vertices in T. And now because in the graph gamma, Hall's condition is satisfied. So Hall's condition in gamma implies that the neighborhood in gamma of S0 union T is greater or equal than the cardinality of S0 union T. And that's the same thing as the neighborhood of gamma of S0 union T greater or equal than the cardinality of S0 plus the cardinality of T, because S0 and T are disjoint. Now, we mentioned before, from S0, there are no edges in this, in B minus N0. I mean, there could be edges from T going that way, that's fine. But so all the edges from S0 end up in NS0. So the neighborhood here splits into the neighborhood in gamma of S0 plus what? Plus the only other contribution to the neighborhood is from the vertices in T, and that is going to be the neighborhood in gamma 1 of T. So this is the left-hand side, which is going to be greater or equal than the cardinality of S0 plus cardinality of T. And now we use the fact that the neighborhood of S0 and the cardinality of S0 are the same. So you can delete them from both sides, and then we get that the Hall's condition is satisfied. So we prove that the Hall's condition is satisfied in gamma 1, and that implies, so let's write it here, that implies that let's write it this way, gamma 1 has a matching M1 that saturates A minus S0. Okay, so there's some matching here M1. And now what we'll do is we take the matching M0 from gamma 0, and we put it together with this matching M1 from gamma 1. And their union is going to be a matching in the big graph, because first, the endpoints on the left cannot overlap. The endpoints of these edges cannot overlap because S0 and A are disjoint. And also their endpoints on the right cannot overlap because those two sets in which these endpoints could live, neighborhood of S0 or B minus neighborhood of S0, are also disjoint. So I'll write it here. We get 9 that M0 union M1 is a matching of gamma that saturates A. And that finishes the proof of case 2. Okay. So again, just to recap, after all this work, these cases, we proved this result that a bipartite graph with partite sets A and B, cardinality of A is less than or equal to the cardinality of B. There is a matching that saturates A, if and only if for every subset of vertices in A, the neighborhood of that subset is in its cardinality is greater or equal than the cardinality of the subset. Now, let me do one more thing before I go and show you the equivalence with what is called SDRs, or system of distinct representatives. And what are system of distinct representative? Let's say we have A1, A2, AN. Let's say we have a bunch of finite sets. And what we would like, we wonder, is there a way to choose, can we choose A1 from in A1, A2 an element of A2, blah, 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 AN an element of AN, such that A1, A2 are all distinct. So this would be, if you can do that, such a collection, such a set, such a, A1, A2, AN, this would be called a system of distinct representatives for these sets, or an SDR for A1, A2, AN. Okay, so is it possible for us to do that? And it turns out that this here's the theorem that the finite sets A1, A2, AN have a system of distinct representatives, have an SDR, if and only if we take for any subset of indices, let's say for any I subsets of indices from the set N, if you take the union now over all I in I of cardinality of AI, so the union not of the cardinality of the sets AI, the cardinality of the union is greater or equal than the cardinality of the set I. And what does this have to do with the Hall's marriage theorem? It turns out that this theorem is actually equivalent to Hall's marriage theorem. Just a different way of stating it. Let me show you how that works. So we have, let's say we have our situation with these sets A1, A2, AN. Our bipartite set, our bipartite graph, we create a bipartite graph in which the set A is the union A1, A2, AN, so all the elements. And over here, we put, oh no, we do it the other way around, I'm sorry. We put here the sets A1, A2, AN. These are the vertices. So the vertices on A are the sets A1, A2, AN. And in B, we take the union from I equals 1 to N of AI. So the union of all the sets A1 and AN. So these are the elements. These are all the elements X. X belongs to A1 union AN. Okay. And then if I have an element X here and I have a set AJ here, I will put an edge between them. I put an edge if and only if X is contained in AJ. Okay. So if I have A1, A2, AN sets, I can build this bipartite graph, gamma bipartite graph. And if this condition is satisfied, this SDR condition is satisfied, the one that I have here, this condition, so the SDR condition, is actually equivalent to Hall's condition in this bipartite graph. Why is that? Well, if I take some subset of a collection of subsets there, so something AI with I in I, something like that. When I look at the neighbors on the neighborhood of this, so I take S to be AI with I in I, the neighborhood of S see on the other side, the neighborhood of S consists of all elements X that are contained in at least one of these sets. So it's the union over all I and I of AI. And now, what was Hall's condition? Hall's condition was cardinality of S at most neighborhood of S. And it turns out, if you look at these two sets here, this is the same as the SDR condition that I wrote it in the opposite inequality, but it's the same thing as the cardinality of I is less than or equal than the cardinality of the union of AI over all I in capital I. So this problem of systems of distinct representatives is equivalent to the one of matchings in bipartite graphs, and is equivalent to Hall's marriage theorem. Next time, we'll talk about some applications of Hall's marriage theorem to group theory and to combinatorics.